Good afternoon, everyone. How are you all? Okay, so we will wait for few 1 or 2 minutes. After that, we will start. Till then, can you please confirm, am I audible and my screen is visible? Okay. So now we will start. In the previous class, what we have concluded the Earth's magnetism and we have completed the magnetism chapter. Earth's magnetism was the most important part of that section. Why I am saying that is important? Because that section of the magnetism is going to be used in electromagnetic induction. So before moving further, before discussing what is electromagnetic induction, let's check out the syllabus of this chapter. What's necessary, what we are going to study in this chapter. So just have a look at the syllabus or what's inside the chapter. One thing is that you can see, first of all, we will start with magnetic flux, like what is magnetic flux. Then we will enter towards electromagnetic induction, that what is electromagnetic induction. And in that portion, we will study some Faraday's experiment and laws. After that, there is motional EMF, self-inductance, and mutual inductance. So don't worry about the topics. We will discuss them each one by one. So right here, starting with magnetic flux. I hope everybody has studied electric flux in electrostatics. There is no doubt about that. So what was electric flux is the same thing with the magnetic flux. So I will not take a lot of time in describing magnetic flux. One thing that you can understand here about magnetic flux, the number of magnetic field lines, or you can say the relative number of magnetic field lines passing through a surface, that you can exactly recall from the electric flux. I don't think there is a problem. So if I recall the formula about electric flux, what was electric flux? This is denoted by phi, and E I am using as a subscript here for electric flux was E dot A. I hope you remember. Now, in the same way, if I talk about magnetic flux, it will be phi, denoted by phi. B is the in subscript, and it will be B dot A, where B is the magnetic field, A is the area vector. What is area vector? Generally, area vector is perpendicular to the surface or perpendicular to the plane of the loop. If I talk about a loop, it is perpendicular to the plane of the loop. What I mean perpendicular to the plane of the loop? That is again very important thing. So before describing that, I will describe each term here. What is A? This is area vector. What is B? This is magnetic field. And this is what magnetic flux. I hope this thing is clear. Now, one more thing. What is the unit of this magnetic flux? And is it scalar or vector? As you can see, this is dot product. So this is a scalar quantity. Unit is what? Tesla meter square, or you can say Weber, denoted by WB. This is the unit. And you can remember this unit Weber. Now again, the main question, what is the area vector? Area vector is always, or I will say area vector, which is A, we will take it normal, or you can say perpendicular to the plane of the loop. So now let's take an example. For example, let's suppose I'm saying that this is our x, y, and z axis. X, y, and z axis. Clear? Y and x. These are our three axes. Now let's suppose there is a loop. There is a loop placed in YZ plane, as you can see this one. This is a loop like that. This loop, you can see it is placed in the YZ plane. So what will be the area vector of this loop? The area vector of this loop will be in the x direction, or you can say perpendicular to this plane. This loop is already in the YZ plane, so perpendicular direction will be, area vector will be in the x direction only. Is it clear? Similarly, if a loop is in the xy plane, then its area vector will be in z direction. As simple as that. Okay, moving further. So it's time to take some question here. Let's suppose this is your checkpoint, what you have learned in this particular topic. So there is a question. Now that's why I was discussing the horizontal and vertical components of the Earth's magnetic field. You can see it right away in the first question. Okay. So I will give you some 20 to 30 seconds to read the question actually. What it says, question says at a given place, the horizontal and vertical components of Earth's field are BH and BV, and the direction is in the positive X and negative Y direction respectively. Okay. That means horizontal component BH is in the positive X direction. So let's suppose this is horizontal component in a region, and vertical component is in the negative Y direction. This is vertical component. Clear? Now this is the field or Earth's magnetic field in a region. It is given in the whole region, or you can say in the whole screen, this magnetic field is present. Now they are saying find magnetic flux linked with a rectangular loop of area A. So that means there is a rectangular loop when it is placed in the XY plane. So one thing that is very clear, I don't think that I need to draw the diagram here. You can clearly understand that if loop is in the XY plane, its area vector will be in which direction? Can anyone answer this simple question? If loop is in the XY plane, area vector will be in which direction? Everybody will say area vector, that is area magnitude is A, and area vector will be in Z direction, perpendicular to the plane. That is K cap. Clear? Okay. Now you have to find the magnetic flux phi. There are two fields. One is horizontal BH, one is vertical. Can you see that for both the fields, angle between magnetic field and area vector is 90 degree. Can you see that? This is in the I cap, this is in the minus J cap. I hope you know these terms, I and J, and everybody knows these simple terms. So what I was saying, that for each magnetic field, whether it's a horizontal component or vertical component, theta is going to be 90 degree. That means we know the formula phi is equals to BA or B dot A, or you can write it as BA cos theta. So theta in every situation is 90 degree. That means flux will be 0. I hope this is very simple to you. This was the first part. Now, the second part says loop is in the YZ plane. If loop is in the YZ plane, then in which direction its area vector will be? in which direction its area vector will be. You will say area vector has a magnitude of A and it is in the YZ plane, so its direction will be in the I cap. That means horizontal. Now again, if I calculate magnetic flux, you can see that for the vertical component, theta is going to be 90 degree. Am I right? For vertical component, theta is going to be 90 degree. So phi for the vertical component is 0, but phi for the horizontal component is going to be BA cos theta. And if you put the values, B field is what? Horizontal BH, area is A, angle is 0. So it will become BH into A. This is due to horizontal field. So total flux will be what? You can add these two vertical and horizontal and you will get BH into A. This is the total magnetic flux in two cases. So from this question, what you can conclude? What you can conclude? The conclusion that you can withdraw from this question that flux is BA cos theta and this flux will be 0 if theta is 90 and this flux will be maximum if theta is 0. So you can make these punchlines in your mind and just write it down. After that, we will move further. If you have any doubt, you can ask. Okay, moving further. Okay, so there is one more question on your screen. Let's try it out for some 30 seconds. Whenever you start a question, just first of all, look at the question, what it is demanding. They are saying that find magnetic flux linked with the square loop. So this is a square loop which has a side L. And this is a long wire which has some current I. Now, as soon as I see the magnetic flux term, the first thing that came to my mind is phi is equals to B A cos theta. Now, if I look closely at this point, B is the magnetic field. And till now, what we have studied that BA cos theta, in which B is the magnetic field, and that B, the magnetic field, was uniform. Now, if you look at this question, this is the long wire, it will produce some magnetic field. This wire will produce some magnetic field. Can you tell me the direction in which this magnetic field will be for this loop? You can simply answer this question that what will be the direction of magnetic field due to this long wire? You will say, sir, the magnetic field, the direction of magnetic field will be inward. How you can find it? We can find it by using right hand thumb rule that we have studied in the previous chapter. Take your right hand, curl your fingers in the direction of point where you want to locate the field, and your thumb will be inward. So you got the direction, field is inward. Now, one more thing, this field or will this field be uniform throughout the loop? You will say, for example, if I take this point, at this point, the distance is A, and at the last line edge, or you can say at this point, separation is A plus L. Can you see that the distance from the wire is increasing? Or you can conclude that magnetic field is decreasing. And if magnetic field is decreasing, that means field is not uniform. And when a quantity is not uniform and you want to calculate that quantity, or you want to calculate a quantity related to that, then what you need to do, there is only one option left with us, that is integration. That is integration. So for integration, how we can integrate the things? The standard procedure for integration that we have learned in the previous classes. What was that? Just take a very small element. This is a area. So just take an area element, like suppose this is an area element I am taking of very small length, let's suppose dx. I have taken a very small element of length dx. Clear? At what distance? At a distance x from the wire. I hope this point is clear. Now what I will do, I will calculate the flux for this small area and then integrate it with the proper limits. Clear? Okay. So before calculating the area, can you see that we need to find the magnetic field? So what is the magnetic field at the location of this small area? You will see that magnetic field will be, what is the magnetic field for a long wire? You need to remember that was mu naught over 4 pi 2I by A. A is what? Perpendicular distance. So at what distance we are calculating? We are calculating at a distance x. This is the magnetic field at this small element. Now, what is the flux? Or I will say flux with small area element. What will be the flux with the small area element? You can easily write it as the small flux d phi is equals to B dot A. What is B? Magnetic field we have already written mu naught over 4 pi 2I by x. This is magnetic field. What is the area of this small element? You can see that length of this small element is L, width is dx. So this rectangular area has a area L dx. This is the area. And you can see that magnetic field is also in the z direction and area is in xy plane. That means its area vector is also in the z direction. So there is no angle consideration, that is 0. Now, as soon as you calculated the magnetic flux for the small area, for complete flux, you can integrate it. And if you integrate it, it will become mu naught over 4 pi 2I by x L dx. Integration is from where? From A. And what is this last distance? A plus L. So you can integrate it from A to A plus L. I hope everybody remembers the integration thing. And if I look at the integration part, what you can do, take some constants outside the integration, that is mu naught by 4 pi is a constant. What is its value? Can you write? Another point is 2IL, which is a constant. 2IL is a constant. What's remaining? 1 by x dx from A to A plus L. Clear? Now, I hope everybody remembers this term, that what is the integration of 1 by x? What is the integration of L 1 by x? You can write it here. Phi is equals to mu naught by 4 pi 2IL, and this is going to be ln x. Ln x, limit is A to A plus L. If you have any doubt, you can ask. Now, if you put the limits, upper limit minus lower limit, I am assuming that you are in class 12th and you know how to put the limits. So without wasting any time, I can easily write it as mu naught by 4 pi 2IL ln of upper limit is a plus l, and if I put the lower limit as minus ln a, so ln a minus ln b, you know that is ln a by b, so it is ln a. This is going to be your answer. The flux linked with the loop or with the square loop is this one. So what you can learn from this question, what was the purpose of this question, was to introduce you one important thing. Whenever the magnetic field is changing, whenever the area is changing, what you can do, you can take a small element, calculate the flux with that small element, and then integrate it with proper limits. That's what you need to do. And this is what the examiner asks you in the exam. I hope it is clear. On this note, I am moving further for the next concept. Now, Faraday's experiment. This is again a very important concept here. What is Faraday's experiment? He actually accidentally done some experiments with the magnets and some coil. Like suppose you have studied it in your classroom that he has a magnet and there was a coil attached with the galvanometer. Like you can see, there was a coil and a magnet suddenly falls on it. This diagram is placed horizontally, but when it happens for the first time, the coil was placed in the horizontal plane on the ground, attached with a galvanometer. This is a galvanometer, and a magnet falls on it. And during the fall, what he observes that galvanometer shows deflection. So in this experiment, what he did, he took a coil. This is a coil, attached it with a galvanometer, and one magnet, a bar magnet, is moved along its axis to and fro. He Once he brings the magnet, then takes back the magnet, brings the magnet, takes back the magnet, and whenever he brings the magnet, a deflection is observed in the galvanometer. When he returns the magnet back to its original position, he observes a deflection opposite to the initial deflection. So try to note down these observation in your mind that something is happening. Like suppose this is a coil. This my hand is a coil. This is a magnet, and this magnet is moving. A deflection is observed in the galvanometer. Like suppose in the right side. When this magnet is bringing back or taken back, then deflection is shows in the opposite direction. We will discuss the direction later, but you can see that deflection is happening and or depending on the direction. Now you can see it in another form like here. Here, you can see that there is a coil attached with a bulb. You can see whenever the magnet is moving, these dotted lines are just electrons. So these electrons flow in one direction. When it moves in the opposite direction, these electrons move in the opposite direction. And as the flow of electrons causes the current, the bulb glows. So this is the first experiment. Now, what are the variations in this experiment you can see from here? I am telling you. Just look at me. This is the coil. This is the magnet. He has moved the coil, moved the magnet towards the coil. Deflection was observed. When the magnet was taking back, the deflection was observed but in opposite direction. Now, repeating the experiment. Now, this time magnet is stationary, but the coil is moving. The same thing happens. There is a deflection. Now, if both are moved together towards each other, the deflection was more. One more thing. One more and final thing. When these two are moved together in the same direction with the same velocity, that means they are moving like this. They are moving like this. Both are moving in the same direction with the same speed. No deflection was observed. And from this, what he concludes, the conclusion was very simple. As you can all see, the conclusion was whenever there is a relative motion between coil and magnet, current is induced. Current is induced. Now, there is one more experiment associated with it that you can see on the next slide. So remember one thing, whenever there is a relative motion, it's not about motion, it's about relative motion. Now, next experiment. In this experimental setup, if I tell you, this is the same coil as in the previous diagram, coil attached with a galvanometer. This is a galvanometer. Now, what changes in this question or in this experiment? He took a coil and attached it with a key and a battery. Now, if you can close the key, current will flow. If you can remove the key, current will stop, right? So, what was the experiment? Initially, the key was off, or you can say switch was off, whatever you want to say. As soon as he closed the key, this is the key. I hope you have seen the key in the laboratories or the switches. As soon as he closed the key, a deflection is observed in the galvanometer. Like suppose it is deflection was like that. And the deflection was for a moment when you turned on the key or when you put the key or when you closed the key, only for a moment there was a deflection. And needle was something, it was stationary before and it deflected and returns back for a moment. There is a momentary displacement or you can say deflection in the galvanometer. Now there is no current. After some time, he removed the key. As soon as he removed the key, the deflection was again observed, but this time in the opposite direction. Again for a moment, but in opposite direction. So these were the two experiments of Faraday's. What you can conclude in all these two situations. In all these two situations, if you look closely, magnetic flux with the coil is changing. Like you can see in the previous diagram here. This magnet has some magnetic field like this. As you all know from the previous chapter, the magnetic field is stronger near the poles and weaker away from the poles. Now, what I am moving this magnet towards the coil. So this pole is reaching towards the coil. And if pole is reaching towards the coil, can you see that the strong region field or the strong field is reaching towards the coil? So again, can you see that flux is changing with the coil? And if flux is changing, so remember that point, flux is changing in the first diagram. Now in the second case, if I talk, you can see that initially at t equals to 0, the magnetic field was 0 because switch was off or the key was not closed, key was open. Now you closed the key. You closed the key. As soon as you closed the key, what will happen? Some current will pass through it. And when current will pass through it, what you can observe, it will create some magnetic field. It will create some magnetic field like that. Or you can say, it will create some magnetic field like that. This field will get linked with this coil. And due to this, some flux is creating, some flux is changing. Initially, there was no flux, and now there is some flux. So, flux is changing with this coil as well. That's why what he concluded, what Faraday concluded, that whenever there is a change in flux, the current is induced or the EMF is induced in the coil. And this induced EMF is known as electromagnetic induction. So, what is electromagnetic induction? Now, if you want to summarize, what is electromagnetic induction? Electromagnetic induction is a process of inducing EMF in a coil, in a circuit, or whatever, by changing the flux in it, by changing the flux linked with it. This is called electromagnetic induction. I have not written the definition. Definition is everywhere on your notebook or on your what you could say in your books. So I don't think it is necessary to write down the definition here. But are you getting my point? What is electromagnetic induction? I hope it is clear. Moving further. So I have discussed the conclusions with you. If you want to write the conclusions, what was it? Whenever flux linked with a coil, I am writing it coil, whatever it may be a loop, it may be a surface, metal surface, flux linked with a coil changes and EMF is induced in the coil. And this process is known as electromagnetic induction. And in short, we call it as EMI. This process is known as EMI. I hope this is clear. Okay, moving further. Now, after discussing the Faraday's experiment, now it's time to discuss the what are the laws of Faraday. As you can see, the creation of EMF is linked with the so what he concluded that he concluded rate of change of magnetic flux. Is it clear? I hope there is no problem with. Suppose they are talking about a coil that we have discussed in the previous question. Let's suppose this is the coil, and in this coil, some EMF is induced due to the movement of the magnet. Assuming this is placed in the YZ plane, some EMF is induced in this coil, and that EMF is given by minus d phi over dt. Now, there will be some current as well. Let's suppose its resistance is R. So, there will be some current as well. What will be the current? I. You can say I is equals to, you know that E by R. This is simple Ohm's law. I is equals to E by R. Just put the values and you will get I is equals to E is what? Minus d phi over dt by R. So you can see that you can also calculate the current in the coil. If you know the EMF, you can calculate the current. And how you calculate the EMF? By finding the rate of change of flux. I am putting this minus sign here, but there is no need to put this minus sign while calculation because we will find another way to find the direction of the current. And that is known as Lenz law. The most important part of this chapter, if I summarize till now, what I have done, we have uh, just calculated magnetic flux. What is magnetic flux? It is similar to the all the questions that you have done in electric flux. all are valid for the magnetic flux. All questions are valid for magnetic flux. So you can practice there. Or if you have practiced enough in the electrostats part, there is no need here. So that is electrostats. That was magnetic flux. Now, second thing that we have studied is the Faraday's experiment. From Faraday's experiment, what you have concluded that whenever the magnetic flux changes, some EMF is induced, and that EMF is given by rate of change of magnetic flux. And if you have calculated EMF, you can easily calculate the current. I hope clear it is. Now, there is time for the concept check. Okay, let's do some question. Question is on your screen. I will give you some 40 seconds to read the question. To the question, what it says. First of all, show that. Okay. If the flux of the magnetic induction through a coil changes from phi1 to phi2, okay, that means flux is changing, then the charge Q that flows through the circuit of total resistance is this much, where R is the resistance. Okay, so no problem. What the question says, they are saying that flux is changing from phi1 to phi2 through a coil. Then they want us to calculate the charge transferred, charge flown through the circuit. Clear? Okay, so charge they are asking basically. The result of this question you will remember as a standard result. This is not a question basically, this is a standard result that you should remember all the time. It will make your life easier because most of the times the question about charge is asked in the JEE and NEET exam. So let's suppose they are saying flux is changing from phi1 to phi2. And if flux is changing, that means there must be, it will take some time to change. Let's suppose flux is changing from phi1 to phi2 in some time delta t. So time is not given, so I'm assuming let flux changes in time delta t. Okay. So what will be the EMF induced in this time? I am not using sign here. That will be delta phi by delta t. I told you earlier that we will use this sign. We will not use this sign because we are going to use some Lange law to find the direction of positive polarity and negative polarity. So don't worry about that. This is what EMF. And if I say what will be the current, I equals to E by R. You can say 1 by R. Delta phi by delta. What is delta phi? Change in flux. Change in flux. Find the direction. We can put the value of delta phi at any time. Okay. Then what is charge or what is charge transferred? What is the relation of current? You know that I equals to Q over T. So Q equals to and is what delta E. In the delta t time, I want to calculate the charge flow. That I delta t, I should put the magnitude will be I is delta 5 by delta t into delta can two is delta 5 by r. This is Sorry for the interruption, guys. I hope I lost some connection there. Okay, so that was the question that I was discussing here. Make or what I can say, just remember this result. This is very important result. Why I'm saying important? The one conclusion that you can withdraw from here, that charge flown through the circuit is independent of time in which flux was changed. Can you see that? The charge flown through the circuit is independent of time. So this is the punchline. You can always remember in a simple question in the NEET examination, they may ask you, or it might come in the form of assertion region question, that charge flown through a circuit is independent of what? Is independent of time. You should remember this line. I hope it is clear. Moving further. Now there comes Lenz law. If I say, what is Lenz law? In one simple statement, just try to remember, just try to figure out the things. The EMF was induced due to the change in flux. Change in flux means what? Flux either may increase or it may decrease. This is what change in flux. So the EMF induced will have such a direction. Are you getting my point? The EMF induced, just listen to me, nothing else, just listen to me. The EMF induced will have such kind of direction that it will oppose the change producing it. Now you know the changes, it might be increasing flux or the decreasing flux. If flux is increasing, that it will try to decrease the flux. If flux is decreasing, it will try to increase the flux. How it will do so, we will describe in this section. So first of all, if I go with the definition thing, what is that? The effect of induced EMF is such as to oppose the change in flux that produces it. As simple as that. Now, coming back to the topic. What is flux? You know that flux is B A cos theta. Clear? So one thing that you should know, flux, how flux can be changed. In three ways, flux can be changed. Number one, by changing the magnetic field. Number two, by changing the area of the loop or the coil. Number three, by changing the orientation of the coil. By changing the orientation of the coil, like suppose if a coil is placed in this position, you see my hand, and if you turn this coil, can you see that it will make some another angle with the field? So by this way, you can also change the magnetic field, magnetic flux. So by these three methods, flux can be changed. Okay. So we will focus each of them one by one. And if we can study all these three terms, then Lenz law is clear. No problem with that. And you can say, oh, complete chapter is clear. Now again, coming back to the topic. For example, we will understand it by some examples. So let's start with the example here. Just try to understand the thing. Let's suppose the lines I am drawing all are conducting. All are conducting. Let's suppose there is a loop P, Q, R, S. This is a loop. And there is a magnetic field as well. And this magnetic field is into the plane. Can you imagine? Magnetic field is going into the screen on which you are watching. Now, this PQ wire has a special arrangement that it can slide. Let's suppose this PQ wire is sliding this way with some constant speed, assume V. Now, again, coming back to the topic. At some time, look at the question. If the wire PQ will move, can you see that the area of the loop PQRS will increase or decrease? If the PQ wire will slide down as shown in the diagram, then the area of the loop will increase or decrease. You will say, sir, area will decrease. Definitely decrease. Clear? At some time it will be here, it will be here. After some time it will be here. So you can see that area is decreasing continuously. If area is decreasing, what can you conclude? That flux is also decreasing. Clear? Very good. Now, what the statement of Lenz law, that it will try to oppose the change. That means it will try to increase the flux. How it will increase the flux? It will increase the flux by creating such a current, or the direction of current will be induced in such a direction that it can support the flux. Now, to support the flux, I will say, can you do one thing? If we can increase the magnetic field, if we can, in area is decreasing continuously, that's some other source. That is some, that area change is created by some external source which we cannot control. It is going to change. Now, only EMF is the process that can induce, or only current is the way by which we can control the flux. So, can you say that to oppose the change in flux, new magnetic field should support original field? Are you getting my point? If current is induced in this loop, that current will also create a magnetic field. So the new current or the new magnetic field should support the original field. That means induced field should be in the inward direction. And as soon as I find the direction of induced field, I am ready to find the direction of current. What you can do now, just put your right hand thumb in the direction of induced field, in the direction of induced magnetic field, or the new magnetic field, you can call it, and curl your fingers. Just put your right hand thumb in the direction of which is into the plane. And as I curl my fingers to close the fist, the fingers, the direction in which fingers are curling is the direction of the current. That means direction of current will be something clockwise. Now, what are the steps I have taken? First of all, I need to find whether flux is decreasing or increasing. If it is decreasing, I will try to increase the flux. How it can be increased? By creating new field which will support the original field. Now, on this behalf, we will do some questions, and you need to answer the questions. Right? Moving further for the next example. Okay. Next example. Okay. Similar kind of example I will not give. Let's take, let's suppose this is a loop. This is placed in the YZ plane. And this is some magnet. And this is the north pole of the magnet. Clear? And this magnet is moving in this direction with some constant speed V. And you need to find the direction of the current induced in this loop. You have some 20-30 seconds to answer. What was the question? Find the direction of current. Find direction of induced current. This magnet is moving along the axis of the loop. Okay. What you can do here, first thing, just try to remember one thing, that this magnet has this is north pole. So the magnetic field lines will be something like that. Or you can conclude that original magnetic field is in the right direction. Can you conclude it that like that? Original magnetic field is in the right direction. And as the pole is moving towards the magnet, I will give you a trick after that. But basic thing you need to understand. As the magnetic pole is moving towards the coil, the magnetic field will increase. That means this magnetic field is increasing. And if this magnetic field is increasing, that means flux is also increasing. So what you need to do? You need to decrease the flux. That means the new magnetic field that is going to be produced should be in the left direction. Should be in the left direction. Now, how I achieve this point? Because flux was decreasing, flux was increasing, and if flux is increasing, I need to decrease it. How I can decrease it? Just create a new magnetic field opposite to the original magnetic field. Opposite magnetic field was in the right direction, so new magnetic field should be in the left direction. What you can do now? You can put your right hand thumb in the left direction like that, and after that curl your fingers. And if you curl your fingers, the direction of the fingers curling will give the direction of the current. This is the direction of the current. What you can write about this direction, whether it is clockwise or anti-clockwise? To write clockwise or anti-clockwise, you need some frame of reference. I hope you remember this thing. If someone is standing here, he will see it otherwise, and someone is standing here will see it otherwise. So what is the standard way to answer? The standard way to answer is always from the magnet side. Is always from the magnet side. So this is not the right person to answer. The right person to answer the question is this one. So how he can see the current? He will see that current is anti-clockwise. कहाँ से? From where? As seen from the magnet. I hope this is clear to everyone. Now, on this note, I will give you some questions. The checkpoint is on the next slide. You can see this is the first question on your screen, and you need to answer. Three options are there: A, B, and C. What is the question? Find the direction of induced current in the loop. So this is the loop. This loop is placed in the XY plane. I am describing the question, nothing else. I am just describing the question. The wire or the long wire is placed along the Y axis, which has a current I, and this current is increasing with time. This current is increasing with the time. So you need to solve this question in your homework. After that, we will discuss. In the next class, we will discuss about that. Just solve this question in the homework. Till then, bye everyone. I will end the session now.